everyone and welcome to my channel. So today we have a question which says that the crystal field splitting energy of CO oxalate 3 whole thrice 3 minus complex is n times that of the chromium oxalate complex. Okay, so we have been given two complexes. One is that of cobalt and another is of chromium, and both having the same ligands, that is oxalate. Okay, and here it is asked that what is the value of n. Okay, so the crystal field splitting energy CFSE has to be calculated for both these complexes, and then we have to calculate the value of n, which is cobalt is n times, the CFSE of cobalt is n times that of chromium. So this value of n has to be calculated. Okay, so here also it is written that assume delta octahedral is much greater than P. So what is P here? The P here is the pairing energy. Okay, so if you have some idea about the crystal field theory, okay, in coordination complexes, then you must be knowing the terms like delta octahedral, CFSE and the pairing energy. Okay, so when delta octahedral is greater than pairing energy, that means pairing takes place. So there is pairing. And what is the meaning of pairing takes place? So it means that both these cobalt and chromium complexes are low spin complex. Okay, now we move on to the ligands in the next step. So here we have oxalate ligand. So if you know the formula of oxalate, then you can understand the coordination number of cobalt and chromium in these complexes. So oxalate is COO minus minus, and here we have oxygen, the two oxygen. So this is the formula, the structure of oxalate as ligand, oxalate ion, and the oxygen here is the donor atom. So two oxygens are the donor atoms, and if there are two oxygen donor atoms in oxalate and we have three oxalate ligands, then that means 3 multiplied by 2. So 3 multiplied by 2 donor atoms, that is equal to 6. So we have 6 ligands. We can say this, that we have 6 ligands. And when this metal ion is coordinated to 6 ligands, then we have an octahedral complex. So this complex is octahedral. Both cobalt and chromium complexes are octahedral. So this is how we can find out the nature of the complex through the number of donor atoms of the ligands. Now, so we have now the full information about the character of these two complexes. These two complexes are octahedral low spin complexes. Okay, now from our knowledge of crystal field theory, we know that in the presence of the ligands influence the degenerate d orbitals to split into two orbitals of T2G and EG. So the d orbitals of the metal ion, they get split into two orbitals T2G and EG in the presence of a ligand field. So if you have some background knowledge of crystal field theory, so you know all of this. Okay, now, so this is the splitting pattern of octahedral complexes. So we are concerned about the octahedral complexes in this question. Fine. And also, what is this energy? So this is lowered by minus 0.4 delta octahedral, and this is increased by plus 0.6 delta octahedral. So this also we know that the CFSE is decreased for T2G by a factor of minus 0.4 delta octahedral and increased for EG, the high energy d orbital, by a factor of plus 0.6 delta octahedral. Okay, now in the low spin scenario, the pairing will take place. Okay, now we have to find out the oxidation state of cobalt and chromium in both of these complexes. So oxidation state. So oxidation state of cobalt, if we suppose that oxidation state of cobalt is X and oxalate has what is the charge on oxalate? That is minus 2, because we have two oxygens which are negatively charged. So charge on oxalate is minus 2, and minus 2 into how many oxalate are there? There are 3 oxalates. So plus charge on the oxalate minus 2 into how many oxalate ligands? 3 oxalate ligands. So multiplied by 3 is equal to the total charge on the complex is minus 3. Is equal to minus 3. Then we have got X is equal to plus 3. So the oxidation state of cobalt and chromium both is plus 3, because for chromium also we apply the same principle to calculate the oxidation state of chromium. So cobalt and chromium. So both have a plus 3 oxidation state. Now you know the electronic configuration of cobalt. The ground state electronic configuration is 3d7 4s2. Now what will happen in the plus 3 oxidation state? In the plus 3 oxidation state, cobalt will be 3d6 4s0. Similarly, what will happen to chromium plus 3? So chromium is 3d5 4s1. And in the plus 3 oxidation state, chromium will be 3d3 4s0. Okay, we have got the electronic configurations of cobalt 3 plus and chromium 3 plus ions both. Now what we have to do, we have to arrange these electrons in the d orbital according to the low spin complex character. Okay, let's start with cobalt first. So let's consider this diagram is for, this splitting diagram is for cobalt. So CO. So cobalt 3 plus has how many electrons? How many d electrons? It has 6 d electrons, 3d6. And since it is a low spin complex here, so pairing will take place. So how? So all the 6 electrons will be in the low energy T2G orbital. So 1, 2, 3, and then here only the pairing will start. 4, 5 and 6. So all the 6 electrons remain in the T2G orbital. Fine. Now what is our next step? Our next step is to calculate the CFSE. So CFSE we calculate. How we calculate? So we have T2G 6 electrons. Then we multiply by this factor minus 0.4 delta octahedral. So minus 0.4 delta octahedral. And how many electrons we have in EG? We have no electrons in EG. So plus 0. So we don't have any factor for EG. So that comes out to be minus 2.4 delta octahedral. So this is the CFSE for cobalt 3 plus. Now similarly we will calculate the CFSE for chromium 3 plus. And so for chromium 3 plus we have 3 electrons in the 3d orbitals. So 3 electrons, they are filled in the T2G orbitals 1, 2 and 3. And now in this D3 configuration there is no scope of pairing. So T2G will carry 3 electrons. Okay. So we calculate delta octahedral, we calculate the CFSE as, so we have 3 electrons in the T2G orbital for chromium 3 plus, and then we multiply that with a factor of minus 0.4 delta octahedral, and then in EG we do not have any electrons, so that value will be 0, and then we get the CFSE for chromium plus 3 ion as minus 1.2 delta octahedral. Okay, let's just go back to the previous slide and check what we had for CO3 plus. So cobalt 3 plus had minus 2.4 delta octahedral as CFSE. Cobalt 3 plus CFSE is minus 2.4 delta octahedral. Okay, and then we have to find out the factor by which they differ. So we just ignore the minus sign. So 2.4 divided by 1.2. So these are the two factors, and then we have 2. So cobalt is, the CFSE of cobalt 3 plus ion is twice or 2 times the CFSE of chromium 3 plus. So the CFSE of cobalt is minus 2.4 and the CFSE of chromium 3 plus is minus 1.2. So obviously cobalt's CFSE is twice as large as the CFSE of chromium 3 plus ion. So that is the question that has been asked to us. So we can write, go back to the question and write the value of N is 2 here. Okay. So that is the answer to this question. So I hope you understood this problem. So we have to, so what we did to solve this problem. So first of all, we understood the nature of the ligand and the meaning of delta octahedral, which is greater than pairing energy. Okay, then we understood that what kind of a complex it is. It is a low spin complex. Pairing will take place, and then we calculated the oxidation state of these metal ions in these complexes. and then we filled the electrons according to the crystal field splitting in the octahedral low spin complexes. So this is how we solved this problem, and I hope you understood the explanation. And if you have any doubts, please write to me in the comment section. And also please like, share and subscribe if my videos are helpful to you. Till then, take care. Thank you so much for watching, and I will be back soon with the next question.